Okay then. Now, let's look at our exercise 5 that we uh, sort of look at it yesterday already. Um, okay, so you should be able to see the slide already, right?
Yes, doctor.
Okay, now this is the exercise that we should, all of us, should have tried out already by now. Because of course, today we are going into new topic already, which is flow through constriction, where the width of the channel would be reduced lah, basically, right? Of course, for today lesson, right, when I said constriction, it means that the width is reducing, so I'm not going to teach about when the width is increasing, but of course the concept is the same. Once you get what we have learned today, the concept applies to whether the width of the channel is enlarged or is decreased, right? Is reduced. Now let's, before we go into the before we go to analyze flow through constriction, we will be looking at the exercise that we have tried out yesterday. So this exercise 5 is a problem of a rectangular channel with flow of 8.74 cusack, and then the width is 5.5 meter. Manning roughness coefficient is given, so we know that we would find our uniform depth of flow using section factor from Manning equation, and then longitudinal slope is given as well. So a broad crested weir is installed. So you know that this is the case of you need to find H mean already, since it is a problem of flow over broad crested weir. Now, the question asks you to find y1, y3, above the weir, y2, and downstream of the weir, y3. So y1, y2, y3. If h, which is the height of the weir, is given as question A is 0.3, question B 0.4238, question C is 0.6 meter. Now let's look at our analysis. Alright, is this too small for you? No, right? You should be able to see all the numbers, right?
Yes, doctor, I'm able to.
Okay, great. Now, I purposely draw out the rectangular channel because I don't want, here's the thing, when you read a question, right, it's good that you highlight what section it is, whether it's a rectangular, triangular, or trapezoidal, so you won't be using the wrong equation. So this is the rectangular section. So for me, if I encounter a problem involving a rectangular section, I would try to use the simplified formula lah. It's easier. Well, the answer will be the same, even though we are using the typical equation. It will be the same. So, I since I'll be using the simplified equation, I know that for rectangular channel, right, most of the equation will be using discharge per unit width. So if you look at it, what I did first is I try to find discharge per unit width. So I have Q over B. So my discharge per unit width is 1.589. Alright. Then I know that for this question, I need to establish my H mean first, because I wanted to know whether, when H at a certain height, what case will it be? Because I know that there are, certain solution available for case 1, 2, and 3. So therefore, H mean will sort of determine whether it is case 1, case 2, or case 3. So the first thing I need to know is, in order to find H mean, I need to know E naught and E mean. Now, E naught and E mean can be computed if we know Y naught and YC. So therefore, the first after I find my Q, discharge per unit width, what I did next is I try to find my uniform depth of flow. So I'm using the suction factor of Manning equation. So I substitute my A, since it is a rectangular, so my flow area is 5.5 Y, which is By. Then my vector parameter is B plus 2Y. So I substitute in the section factor. So I have try and error. So I got depth of uniform flow equals to 1.302 meter. So I hope you are looking at your solution and we are going through it together. If you have problem, if you think my solution, there's something wrong with my solution, let me know. Then the next thing we would do is we wanted to know what is the critical depth. Now it doesn't matter if you want to find YC first, then why not? It doesn't matter. For me, as long as you have both parameters available, then it should be fine. Then depth of critical flow is, for rectangular, I can use this formula, which is cubic root of Q squared over G. So I have 0.6361 meter. Then what the next thing I wanted to know, because I don't know whether it's case 1, 2 and 3, but I know that for case 1 I need to know whether the upstream is subcritical or supercritical. Okay, because for case 1 Y2 actually depends on upstream condition, whether it is subcritical or supercritical. So I compare Y naught and YC. Apparently my Y naught is greater than YC. So the initial condition is in subcritical state. Alright. Okay. Then the next step, it should be to find E naught and E mean lah. Alright. E naught is Y naught plus Q squared over 2GY squared. Now I'm using this formula because this is a rectangular section, so I can use my discharge per unit width formula. So I kind of simplify it. So I have my specific energy equals to 1.378. Look at all my numbers. I'm using it to 4 significant numbers. And then minimum specific energy is 1.5 YC, or it's actually 3 over 2 YC. So you have there 0.9542 meter. So we know that, of course, E naught should be greater than E mean lah, because yesterday I told you already, E mean is the minimum specific energy. So you won't get E naught less than E mean. If you get E naught less than E mean, there must be something wrong already with your answer. Alright, so therefore, H mean will always be positive because you know E naught is greater than E mean, right? So H mean is E naught minus E mean. So you have 0.4238. Now, here's the thing, the formula might be provided to you. For example, like H mean equals to E naught minus E mean. But for me, if you can draw out, the diagram, either the sketch of the flow over broad crested wheel itself. If you understand what the specific energy is about, which is measured from the bottom of the channel, and you can draw out the curve, EY curve, alright, the specific energy curve, you should be able to extract this formula from those curves already. Okay, so you don't have to memorize it. For me, I just, draw it out. I know already how to get this formula. Up till now, I never go and memorize all this formula, right? I actually get it from sketching. Okay, because everything is there. Once you understand the theory, it should be okay. So H mean, we have calculated H mean to be 0.4238 meter. Alright. Now, coincidentally, question B give you H equals to 0.4238. So question B is actually case 2 already. Now let's try case 1 first. Okay. Case 1. Okay, A, let's look at A, which in fact is case 1 lah. If H is 0.3 meter, you know, when H is less than H min, it is case 1. Look at it, I purposely draw an EY curve there because I wanted to know, I tend to sketch out because I can, by sketching this out, I can actually get my formula already. I know that my E2 is actually my E0 minus H. Okay, so I can get my E2. Or basically, if you draw your sketch of the flow over the broad crested wheel, right, you know that your E0 is actually E2 plus H. Okay, if, or from the bottom, it should be H plus E2 lah. It should be the same. All right, now A, if H is less than H min, so case 1. Yesterday, we already looked at the table of summary, right? For case 1, Y2 is not YC, so we need to find Y2. Okay, so this is a second, I'm running out of battery. Okay, now for case 1, all right, Y2 is not Y2 is not YC. Okay, so therefore you need to find your Y2 already. But we do know that for case 1, Y1 is equal to Y0 and Y3 is equal to Y0. Therefore, if you look at it, the first line that I put under my H equals to 0.3 meter there, right? It's actually, I put there Y1 equals to Y3 equals to Y0 equals to 1.302. I need this statement because I actually, this is a second. Okay, this guy here. By the way, did you see I'm drawing something on the PowerPoint? Anyone?
No, doctor.
Oh, okay, then I cannot do. Okay, then it's okay. Then if you cannot see, then it's fine. Okay, now, all right. So for case 1, you know that Y1 is equal to Y0 and Y3 is equal to Y0. Therefore, I wrote there Y1 is equal to Y3 equals to Y0 equals to 1.302 meter. Okay, that's it. Now, we need to find Y2. To get Y2, we need to know what is our E2. Now, E2 is equal to E0 minus H. So, I have E0 already. I also have H, which is given 0.3 meter. So, my E2 is 1.078 meter. Now, to get Y2, I'm going to substitute E2, alright, and also my Q into the specific energy formula. So, substituting, I need to solve this formula, alright. So, I need to do try and error. So, I have, using your calculator and solving it, you have Y2 equals to 0.9285 meter, right? So, now, actually, am I right? You should get two values of Y2. One is in supercritical, which is less than 0.4, your YC, which is 0.6361 meter. The other Y2 is greater than 0.6361, greater than YC lah, what I mean. But which one is your answer? Your answer should be Y2 greater than 0.6361 and less than 1.302 meter. Why? Because your initial Y0 is subcritical, so therefore your Y2 should be in subcritical as well. I purposely draw out the arrow down, alright, because it doesn't change from critical flow yet. It still remains the same state of flow, which is subcritical. Alright, so therefore your Y2 is 0.9285 meter. If you get a value less than 0.6361 meter, there should be another value that will give you specific energy as 1.078 meter too. That is not the right answer. I'm not giving you marks there. You need to press solve again to get this answer, which is 0.9285 meter. So far, any question? Clear, guys?
Yes, clear.
Okay, alright. Now, okay, that's it. For this question, right, normally if they ask you to find depth of flow, Y1, Y2, Y3, you already give all the answers already for part A. That's it. Okay. Now, part B. Question B. Question B asks if the height of weir is 0.4238 meter. Okay. So what would be your answers for Y1, Y2, Y3? It is case 2. So therefore, your Y1 equals to Y0, your Y3 equals to Y0 equals to 1.302 meter, and your Y2 equals to YC, which is 0.6361 meter. That's it. You give all the values already, Y1, Y2, and Y3. That's it. You have the answers. Then for question C, what if the height of weir is 0.6 meter? Now, H equals to 0.6 meter is greater than your H mean, which is almost 0.42 meter. So, therefore, it is case 3. For case 3, you know that your Y2 is equal to YC, which is 0.6361 meter. Okay. The only thing I do know is Y1 and Y3. How are you going to get Y1 and Y3? You see, I sketch it out. If you have H, you plus a value, right? You are going to get an E, right? You are going to get higher. Even you plus E mean, right? It's going to get higher than E naught. Okay, therefore, you have a new specific energy which is greater than E naught. By how much is your new specific energy is E min plus H. Okay, which becomes E13 prime lah. Because it's actually, it represents specific energy for location 1 and location 3. And the prime means the new one lah, basically. Now, so therefore, if you look at the EY curve that I draw, right, I have the formula there already. E13 is equal to E min plus H. So therefore, my specific energy is 1.554 meter. Alright. So I'm using this specific energy. I substitute it into the specific energy equation. I solve for Y1 and Y3. Because we know that solving this equation here, the nonlinear equation here, is going to give me two answers. Remember yesterday we said for case 3, your Y1 is always subcritical flow. Your Y3 would always be supercritical flow. Therefore, your Y1 should be greater than Y3 lah. And of course, rule of the thumb is Y1 should be greater than your YC, and your Y3 should be less than your YC, which we found the answer to be agreeable to that statement that I mentioned just now. So therefore, your Y1 is 1.497, Y3 is equal to 0.334. Now, remember this. Maybe when you solve for the expression of specific energy, you only get one answer. But I believe you have to press solve another time, you'll get another answer. If you don't get it, you should discuss it among your friends. Because I truthfully, if you ask me to help you with your calculator, I have never used that type of calculator before, because my type of my calculator is a different model, so it cannot key in all those equation. All right. Now, I hope you understand the exercise for yesterday's lesson. So today we are going into another new topic, just to end our chapter 3. All right. If you have question, of course, you can always ask me afterwards, all right? Now, I did explain a few slides already. Flow through on flow through constriction. This is the examples. Okay. Alright, I think I've gone through this. Okay. Now, yesterday we learned about H min. That means the minimal height where critical flow would occur. For in today's class, right, we are going to learn about what is B max. That means the maximum width where critical flow would occur lah at a certain location where it has constriction lah, which is location 2. Now, when I mention about maximum width, that means it's the maximum already. So the more you reduce the width, that location would remain to have critical flow. But remember, in our case, right, today, the width change. When the width change, discharge per unit width change. When discharge per unit width change, remember your YC is actually directly, it's actually perpendicular to, not perpendicular, proportional, is directly proportional to your Q. So therefore, if Q increases, your YC increases as well. So it changes according to your discharge per unit width. Okay, I'm going to skip this diagram. Now, most probably this diagram will be provided to you in your test or your final exam. But of course, you need to understand it in order to use it. Now, I'm going to, okay, let's look at this slide here. It's actually a summary, okay? If you look at it, it's almost similar to the case of flow over broad crested wheel. You have, on your first column, you have the condition of upstream flow where for case 1, you also need to establish whether it's subcritical or supercritical flow. So once you have established it by comparing Y0 and YC, now here's the thing. I put here YC not because you are going to have two YC. One is YC when the B is B0, because at location 2 your B would be reduced. So therefore sometimes I call it B2. So B2 has a different YC. Remember I said because your Q changed already, right? So your YC changed already. So therefore, here I'm using YC0 to represent the width of the initial width of a channel. So here we also have on your first row, right? You also have case 1, case 2, and case 3. Okay. Now, case 1 is when your B2 is greater than B max. So therefore, look there. At location 2, the flow is not critical flow yet. And then you keep reducing the width. Imagine if you keep reducing the width, it will come to a time when it reach B max. That means the maximum width where critical flow would occur at that location. Location 2 lah. Right. So therefore you get case 2 already. When you have case 2, when B2 is equal to B max, your Y2 is equal to YC2. I use YC2 because YC at location 2 is different from your YC at location 1 and not. Okay, because the width is different, the width of the channel. Okay, then you keep reducing the width. So now your width at location 2 is less than B max. At that location 2, your flow would remain critical flow. But of course, your Y2 is another YC already. It is not the same as your YC2 of your B max. because it depends on your B2, alright? Of course, when I explain this, probably it's best to understand if you do some exercises. Okay, here's the thing. Let's look at the, the sketches. Okay, for subcritical and supercritical, you have 3 sketches, right? For case 1, case 2, and case 3. Here's the thing. For case 1, you know already, it's similar to yesterday's flow broadcasted via. For case 1, y1 is equal to y0 and y3 is equal to y0 as well. But your y2 is not yc2. For case 2, y1 also equals to y0 and equals to y3. And your y2 is equal to yc2. That means it's critical flow lah. That means y2 is equal to yc lah. For case 3, yes, your y2 is equal to yc. But, okay, your y1 and y3, you need to find new one. Similar like yesterday's case. Now, your y1, new y1 is always subcritical, and your y3 would always be supercritical flow condition. Alright. Now, how are you going to find your new y1 and y3? Let's take a look at one of the. I'm just going to skip this first. Alright. Okay. Let's look at this slide here. You probably don't have this slide. Okay. By the way, if you are missing any slide, if I forgot to share any, additional information that I put in the slide, let me know which info that you need, which slide that you need. Okay, for example, this one, let's look at an example of a rectangular section, assuming your discharge. This is the discharge, not the discharge over unit width. So let's assume this discharge to remain constant throughout the channel. But of course, if you are looking at discharge per unit width, it will change. Alright, it depends on your B. Okay, so this discharge Q will remain the same throughout your channel, which is 20 meter cube over second. So assuming initially throughout the channel my width is 3 meter, so I have this specific energy EY curve here. Alright, I plotted it against Y, and I have my E equals to Y plus Q squared over 2GA squared lah. Alright, this equation here, this specific energy equation is used for all section. Now, for this case, assuming, okay, because I didn't show what is my Manning or longitudinal slope or my Chasey expression, right? So, assuming my E0 is equal to 5 meter. Okay, initially, that means the initial specific energy is 5 meter. Okay, now, I said at location 2, I'm going to reduce my width of the channel. Let's reduce it to 2 meter. So, here's the thing, this blue curve is when my width is 3 meter. That means, and then at location 2, I reduce the width of the channel to 2 meter. Okay, so I have a new EY curve, but this purple curve only applies at location 2 when my B is 2 meter. But at location 0, 1, and 3, I still would be referring to my blue line curve. I hope you understand, because this EY curve here, I got it from my Q and B. You see, I have Q squared over A squared, right? That A actually is influenced by my B. Okay? Now, then I said, remember this purple line, okay, is actually case 1. I actually wanted to show that this is case 1. Now, at which point it will be case 2, okay, is when, okay, look at it. My minimum specific energy of my B2 case is actually falls on my E0. Okay, Now, here's the thing. Now you know how to get your Bmax already. Okay, the, the concept is Bmax, okay, is when critical flow start to occur at location 2. Therefore, you would have E mean. Your E mean is actually would equal, you will get your E mean at location 2 to be equal to your initial specific energy at location 1, 0, 1 and 3. Okay, so this E mean here is actually at location 2, the green line is at location 2. Now, let's say if I keep increasing, so this will be your Vmax lah basically. And I said I keep increasing the width at location 2, okay, to 0.9 meter, I'm going to have this curve, which actually would remain E minimum, but I have new E, basically I need to find new E already because it's actually increase, it's actually exceeding my E naught already. So therefore, I need to find my new E, which is equal to E13 prime. Now, how are we going to find it? Okay, here's the thing. Let's go back to this slide here. Okay. If I said, how am I going to find it, right? Okay, you see, you can actually get it right from this formula. Actually we yesterday the formula that we used, right, is actually for this case we actually use it in reverse form lah basically. All right, we are looking at, we need to find our E13. How are we going to find E13? We need to find our Qmax. All right, how are we're going to find our Qmax? We are going to determine our YC2. How are we going to determine our YC2? We already have our Q and B, Bmax. All right. Okay. Now, let's go back to case 1. So let's look at the formula here. Okay, for case 1. Okay. I hope. Here's the thing. Let's look at the EY curve. The dashed line represents when your location 2, your width at location 2 is reduced up to a point where the flow start to becomes critical. Therefore, the width is known as Bmax. When your E mean becomes is equal to E naught lah basically. So for case 1, your specific energy is actually, the line is between your Bmax line and your B naught line. Okay, so therefore it's between that. So how are you going to find your Y2 is, okay, now since your B2 is reduced, but it is still greater than your Bmax, you can actually find your Y2 based on, your Y2 is actually you actually can find your Y2 your Y2 based on your Q, where your Q is actually your discharge, you divided by your B2. Then you can find your Q. Alright, okay. Of course, once you find your Q already, you can find your YC, and then you can find your Y2 already, okay? So let's look at one exercise. It's easier for me to explain to you. Okay, now let's look at one activity here. Activity 3.8. There's a bridge which is built across a 50-meter wide channel or river, okay, which has discharge of 200 meter cube over second with depth of 4 meter. Now, the depth is given as 4 meters. So we are using this depth as Y naught, the uniform depth, right? The depth of uniform flow. Now, for reducing the span of the bridge, right, what is the minimum width of channel? Basically, they ask you to find Bmax. Okay, such that upstream water will not be influenced. Now, what do you mean by would not be influenced? Look at this. For case 1, your upstream flow remain the same, right? Okay. For case 2, okay, I think I should show this. You see, case 1 and case 2, your upstream flow depth remain the same. But for case 3, it increases. It has backwater. Now, if this is increased as much as where it will flood your upstream, that is not good. It is actually known as choking. For flow over broad crested weir, you would have the same thing too. For all the case 3, where you have backwater, right? If you reduce the width too much, you would have backwater too high that it would spill over your river bund or your drain. It will cause flooding. It is also known as choking, which is explained on your last slide in this chapter, the phenomenon choking. Alright, let's look at our exercise. Okay, now, in order to find Bmax, right? Okay, I know that if I want to find my Bmax, I know that basically I need to find my B at location 2 where critical flow start to occur. Okay. So how am I going to find it? Okay, I need to know my E naught first. Then I'm going to equate my E min 2 equals to my E naught. Okay, therefore, the first thing that I need to know is I need to find my E naught lah. Since Y naught is given, if Y naught is not given, you need to find your Y naught. Okay, so therefore, Y naught is given as 4 meter. But of course, if it's case 1, now for this case, you probably don't need your YC naught yet. Okay, but this YC naught, you want to determine whether that flow is subcritical or supercritical. So you said you want to find Q naught, and then you want to find your YC naught. Your Q naught is Q over B. Why am I using my subscript O or Q naught there? Because I want to find my YC naught, alright? So I have Q naught equals to 4 meter cube over second per meter. Then my YC naught is cubic root Q squared over G. I have 1.177. Okay, Y naught greater than YC naught, so it's a subcritical flow. Okay, this is, I already explained this. YC changes based on Q. Alright. Now, okay, I think I better show everything. Okay. Now, the next step would be to calculate E naught lah, because I mentioned that your E min 2 at Bmax should equal to E naught. So I have E naught equals to 4.051, solving the specific energy equation. So with Bmax, look at this. When B2 is equal to Bmax, alright, your E2 is equal to E min. That means you know that it is when E is E min, alright, and your Q is Q max. With no energy loss, E min is equal to E naught. Alright, this is extra explanation basically. Okay, now, so I said E min is equal to 4.051. Okay, now what is my YC then? Okay, my YC, remember yesterday, that's why I said for this analysis, right, for flow through constriction, we are actually using our formula, using the same formula. It's just that we are finding different parameter. For example, yesterday we are looking at, we need to find E min. This time we need to find our YC based on our E min, because we know our E min first. So yesterday we are using E min equals to 3 over 2 YC. Today, since we know our E min, we want to find our YC already. So YC at location 2 is 2 over 3 E mean. So therefore YC2 is 2.701 meter. You know, you can plot out your EY curve and then, you know, sketch where the location on your y-axis 2.70, where is your YC not, things like that. Of course, your YC2 should be higher than your YC not lah, because your B2 is smaller than your B not. Okay, then now since we already have YC2, we can actually from YC we can get our B max. Okay, now we know that, okay, our YC is cubic root of Q squared over G. So we rearrange this formula. We wanted to get our Q. Since our Q, if you look at the last line, right, Q is equal to Q over B. Then we rearrange this equation, we can get our B max already. Let's go back, alright. Once we get our YC2, okay, once we know our YC2, we can get our Q max, where Q max is square root of y to the cube power, y cubic power. Then Q is equal to 13.9. Based on our Q, since this is a rectangular section, B max is equal to Q over discharge over unit width. So I have my B. Now this B is actually B max because we set E mean 2 equals to E naught. So we have our B max 14.39. Remember, if our B at location 2 is less than B max, is case 3. If our B2 is greater than B max, is case 1. Okay. Now, activity 3.9. For activity 3.9, you need to find Y1, Y3, and Y2. Okay. Now, it's the same value that I give for activity 3.8, where you have bridge, the width is the same 50 meter, the discharge is the same 200, the depth of uniform flow is the same 4 meter. Now, what if the width of the channel at location 2 is reduced to 30 meter? Just now we found that our B max is 14.39. So this should be case 1. Am I right, guys? Are you still there? Because
Yes,
our
Doctor.
B2 is greater than our B max, right? I know actually, because I'm so excited in explaining it. I might go very fast, but if you try your exercise, you should be able to understand it further lah. Alright. Now, this should be in case 1. So actually, for step 1, right, we have done it. Alright, in activity 3.8. So I'm going to skip this. Okay. This one also, right? Similar. Alright, we have done this. Okay, I just copy this again. Now, this, since B2 is 30 meter greater than B max 14.39, so we expect this to be case 1. Now for case 1, we know that Y1 equals to Y0, Y3 equals to Y0. That means downstream and upstream doesn't change. They don't change for case 1. But the depth at location 2 changes because the width changed already at location 2. Now how are you going to find Y2? Alright, so I said there, I say E2 equals to E0. Now let's look at this. This is where, okay, here's the thing. I cannot show it to you. Here's now imagine this. At your location 0, 1, and 3, you are using the blue line, the blue specific energy curve. But at location 2, Your Y2 is actually, you need to read it from the purple line or pink line, pink curve. Because your B actually, due to the change in your B, it would have a new specific energy already, okay, which is the pink curve. So therefore, your Y2, the Q that you are using to get your Y2 is based on the pink line curve. When you solve your specific energy equation, right, the Q is different from your Q naught already. So let's look at the solution, okay? Okay, here's the thing. Now, E2 equals to E naught. Okay, remain the same, but different Q already, because of course there is no energy loss, right? So E2 is equal to E naught, 4.051 meter. At B2, okay, you solve this specific energy equation, but look at your Q. Your Q is 200 divided by 30 meter. Okay, remember your initial width is 50 meter, right? Okay, so therefore, if you are using different Q, you will expect your Y2 is actually different from your Y1. Is going to be less than your Y1 basically. So your Y0 is going to be less than your Y0. So your Y2, you do try and error solving it, you'll get your Y2. Now there are two answers. One is subcritical. Sorry, your answer for 0.8399 is supercritical state. Your Y2 equals to 3.902 meter is a subcritical state. Which one should be your answer? Your answer should be in subcritical state. Remember, initial condition is subcritical. Therefore, for case 1, your answer should also be the same condition, which is a subcritical. If it is initially supercritical, therefore case 1, your Y2 should be in supercritical. But in this case, it's subcritical, right? So therefore, Y2, the answer is 3.902 meter. Now, you would ask me, if you have in your test or exam, right, if you are given such a question, if you give me both answers, am I going to give you correct? I'm going to minus some marks because you are not sure which depth is the correct depth. Alright, so I'm also not sure whether I should give you full marks or not. Alright, so I'm going to minus 1 mark. Alright, if you are giving me both answers, you should only give me one answer. Alright, now for activity 3.10, I think I'm going to spend another few minutes. Alright, then at the end of the slide, there's one exercise where you can do it. And then I believe I already posted assignment 3. You can solve it, and I think the submission is due 25th November, if I'm not mistaken, but I'm going to check again, right, which is a week after your test lah. Alright, and your test only cover chapter 1 and 2. Okay, now let's look at activity 3.10. You have a rectangle channel, 2 meter width. Of course, this channel is relatively smaller than the other channel, the earlier exercise, which has about 50 meter width, right? Okay, and of course, relatively you have a smaller discharge, which is 3 meter cube over second. Normal depth is 0.8 meter. This is also why not. At downstream of channel, the width of the channel is to be reduced, so which is location 2. Now determine width of maximum constriction. Therefore, you need to find Bmax. For part A, find Bmax. For part B, calculate the depth of flow. That means you need to find Y1, Y3, and Y2 if B2 is equal to 1.2 meter. Now you don't know if B is equal to 1.2 meter is whether it's case 1, 2, or 3, right? So therefore, you still need to solve part A first, alright? Now, in order to solve part A, of course, the concept would be you need to find your E naught. Once you have your E naught, you say when B max occur, your E min at location 2 should be equal to E naught. Then you can solve the rest, alright? Now, let's look at this. So, I check, okay, what subcritical, because this, whether it's subcritical flow or supercritical flow, you need it to solve for case 1, actually. And then, step 2, alright, find E naught. Because I need to find what is my B max, right? Once I find my E naught equals to 0.9792, yeah, I'm solving it for YC. My YC is 2/3 of E min, which is 0.6528. Then, once I have my YC, I can find my Q max. My Q max is square root of GY to the cube power. Okay, then I have 1.652, alright, meter squared over second. The unit is the same, meter cube over second per meter is the same as meter squared over second, alright. Then B max is Q over Q lah. Okay, I just rearrange the expression. I have B max equal to 1.816 meter. The question of where you need to find 1.2, right? So which case it is when B2 is equal to 1.2? Anyone? Ho Yan Mei.
Yes, doctor.
If B2 is equal to 1.2 meter, if you compare it with B max, what case would it be? When B2 is less than B max.
Case 3.
Yes, correct. Case 3. Correct. No, I think because our class is too long, right? You lost focus already. That's why I try to make it maximum 1 hour only, right? Okay. So when B2 is less than B max, because it's maximum already, right? So when it's less, it still would be critical at location 2. So it's case 3. So it is a case 3. Okay. Now for case 3, you need, there will be new Q max. How do you find your Q max? New one is, of course, your discharge, which is the initial discharge divided by your B2 lah. Okay. So therefore, look at step 3. New Q max is Q over B. So you have 2.5. Then your YC2, okay, is cubic root Q squared over G. You have Y2 0.8605. Then you have new E min, which is 3 over 2 YC2. Here's the thing, once you have your new E min, you can get your new E13 using this E min. Remember, your E min 1 is actually increases. It actually greater than your initial E naught already. So therefore, your E13 would be greater than your initial E naught as well. Okay. So now your new E1 min is 1.291. In order to get your new Y1 and Y3, you are going to use this value. But at location 2, you have your Q max equal to 2.5. But if you want to find your Y1 and Y3, you need to use Q naught, because remember, your your Y1 and Y3 still remain on the initial curve, your initial specific energy curve, having the same Q naught. But, of course, you are utilizing this E min, Okay, so your new E1 and E3 bit is equal to E min, therefore, you substitute, okay, here's the thing. Look at this specific energy where I substitute my Q naught equals to 1.5, which is the initial Q naught. Okay? Therefore, I solve the expression. I have two alternate depths. Y1 and Y3. I told you before, Y1 should be subcritical depth and Y3 should be supercritical depth. Alright, so there you have it. Okay, you have Y1 equals to 1.213 and Y3 equals to 0.35 meter, right? So, I think you should try activity 3.11. Okay, I have sketches there just to explain, and there are actually quite a number of exercises. Of course, the last. Okay, now you have to try your own exercise 6. I'll be providing you the answer scheme. I guess next week lah. Alright, before our revision class. You try it out first. There would be 3 cases as well for you to try out. Okay. And then the last slide talk about choking. I mentioned it earlier that actually choking is when the flow cannot flow through. That's why you have backup of water behind upstream lah. Okay, so that is known as choking lah, which occurs in case 3 when flow go over broad crested weir and when flow go through constriction lah. Alright, I'm going to end my class, okay, because it's too long for us already. I think you would lose focus already by now. Okay, do you have any question?
Doctor,
Yes.
I wanted to ask for the test is only chapter 1 and 2 only, right?
Yes, correct. Chapter 1 and 2 only.
For our revision class, we are focusing on which chapter?
Chapter 1 and 2.
Oh, thank you, Doctor.
You know what? When you ask me revision, right? Before our class, most probably a day or 2 before our class on Tuesday, I'll be giving you a set of questions for you to try out, so that during our class we would go through the answers, and I want you to try out first, then we will compare our answer. Is it okay?
Okay, Doctor.
Alright, okay. Only chapter, we will focus on chapter 1 and 2. Okay, any other question? Anyone? Don't tell me you fall asleep already. Okay, then if you don't have don't have question, then I'll see you next week. All right.
Thank you, Doctor.
All right. Take
Alright,
care.
Doctor.
Bye bye. All right.
Thank you, Doctor.
All
Thank you,
right.
Doctor.
Try assignment
Thank
3.
you, Doctor.
Okay.
Thank you, Doctor.
All right.